Welcome to lecture 40. This is week 8 and we have been talking about introduction to linear programming problems. So, in this week we have introduced linear programming problems, then we have discussed about graphical method of solutions, which is essentially convenient only for two variable problems. In this lecture, we will talk about more on standard form of linear programming problems that we have discussed in our previous lecture. So, we will introduce certain definitions related to the standard form of linear programming problem, and then we will discuss about solutions of set of linear equations, say using Gauss-Jordan elimination method that will lead to the canonical form of the systems of linear equations. These discussions will lay the foundation for our discussion on simplex method that we will cover in the next week. So, in matrix notation, we have presented a linear programming problem in standard form as maximize or minimize z equal to C transpose x subject to x equal to b, x greater or equal to 0, b greater or equal to 0. A is m by n matrix, x is n vector, C is n vector and b is m vector. Now, we will introduce some definitions. Some of them you are already familiar with. So, we will review some of those definitions you are already familiar with. A feasible solution is a non-negative vector x that satisfies the constants a x equal to b. So, these notations are related to the problem formulation maximize z equal to C transpose x subject to x equal to b, x greater or equal to 0, b greater or equal to 0. A feasible solution is a non-negative vector x that satisfies the constants a x equal to b. A feasible region denoted by S is the set of all feasible solutions. So, mathematically we can write S equal to x such that a x equal to b, where x is greater or equal to 0. If the feasible set S is empty, then the linear program is infeasible. An optimal solution is a vector x star that is feasible and its value of the objective function C x star is greater than any other feasible solution. So, if x star is optimal solution, it will be feasible and the objective function value at x star, that is C x star, will be greater or equal to C x for all x belonging to the feasible region S. The optimal value of a linear program is the value of the objective function at the optimal solution. Thus, if x star is the optimal solution, then z star equal to C x star is the optimal value of the linear program. If a linear program has more than one optimal solution, it is said to have alternate optimal solutions. In this case, there will exist more than one feasible solutions having the same optimal value z star of the objective function. The optimal solution of a LP or linear program is said to be unique when there exists no other optimal solution. So, there is only one optimal solution. When a linear program does not have a finite optimum, it is said to have unbounded optimum. Then maximization of Z will lead to plus infinity, minimization of Z will lead to minus infinity. You can go on increasing or decreasing the objective function without any bound, depending on whether you are solving a maximization problem or minimization problem. Now, let us discuss the solution of system of linear equations. First, let us consider a square system. By square system, I mean I have a system of n equations with n variables. So, there are n variables and then n equations. So, the system can be solved uniquely. The system can be easily solved because you have n variables and n equations. So, the equations are presented as a11 x1 plus a12 x2 up to a1n xn equal to b1 and so on and so forth, an1 x1 plus an2 x2 plus ann xn equal to bn. It is a square system. So, there are n variables and n equations. So, you will have n rows of equations and there will be n columns of these variables. This system of equations will not be altered under a certain set of elementary operations. There exists a set of elementary operations which, when we apply on this set of linear equations, the system will not be altered. That means, the solutions of the transformed set of equations and the solutions of the original equations will be same. So, let us discuss these two elementary operations. Any equation here is replaced by the equation k into here, where k is a non-zero constant. So, pick up any equation. Let us say I have picked up the second equation. If I replace this equation by multiplying these equation by a non-zero constant, the system of equations will not be changed. So, this is one elementary operations, that you can replace a row by a multiple of that row. Second elementary operation, any equation here is replaced by the equation here plus k into Es, where k is a non-zero constant and Es is any other equation of the system. So, this tells you that I can replace this equation number 3 or third row by sum of third row and let us say a multiplication of the second row or any other row. So, the third equation or the third row can be replaced as sum of third row plus let us say 2 into second row. If I do this, the transformed set of equations and the original set of equations will have same solutions, and that is what we mean when I say the system of equations will not be altered. So, these two elementary operations can be performed on the set of linear equations without altering the solutions. So, first one is any equation can be replaced by a multiple of that equation. You have to multiply that equation by any non-zero constant and the equation can be replaced by a multiple of that equation. Second elementary operation is any equation can be replaced by a sum of that equation and a multiple of any other equation. So, when I have this set of linear equations and I perform those two elementary operations, it is possible for me to express this set of equation in a form known as canonical form. And if you closely look at in this canonical form, the first row, that means the first equations, has coefficient 1 for variable x 1, that is first column, and all other coefficients are 0. Right hand side b 1 has now been replaced as b 1 double prime, because those elementary row operations has been performed. So, essentially the first equation is x 1 equal to b 1 double prime. Similarly, in the canonical form, the second row has been transformed to a row where only x 2 has coefficient equal to 1, all other variables has coefficient 0. So, essentially making this equation as x 2 equal to b 2 prime. This continues, and the last row, that is nth row, because you now have n cross n matrix, the nth row has all the coefficients 0, coefficients for x 1, x 2 up to x n minus 1 0, and the coefficient of x n is 1. So, this equation is essentially x n equal to b n double prime. So, it is possible to transform the original set of linear equations to a canonical form as shown. Operation at each step to eliminate one variable at a time from all equations except one is known as pivotal operation. Note that in the canonical form, each row has only one variable, because all other has been reduced to 0. In the canonical form, if you pick up any row, only one variable has coefficient 1, all other variables has coefficient 0. Operation at each step to eliminate one variable at a time from all equations except one is known as pivotal operation. Number of pivotal operations are same as the number of variables in the set of equations. So, the system of n equations in n variables were converted to canonical form after n pivotal operations. Transform set of equations through elementary operations is equivalent to the original set of equations. We discussed that these elementary operations do not alter the set of equations. In fact, they do not alter the solutions of the original equations, because the transform set of equations that we obtain through elementary operations is equivalent to the original set of equations. Thus, the solution of transform set of equation is the solution of the original set of equation. Now, if you look at the canonical form, the solutions are readily obtained. From the first row, you obtain the solution as x 1 equal to b 1 double prime. From the second row, you obtain the solution as x 2 equal to b 2 double prime. From the third row, you obtain it as x 3 equal to b 3 double prime. Similarly, from the nth row, you obtain the solution as x n equal to b n double prime. So, the solution can be easily obtained as x I equal to b I double prime for all values of I equal to 1 to n. So, once you can convert the solution once you can convert the system of linear equations into its canonical form, you can obtain the solution very easily. So, here is the general procedure for transformation of the set of equations to canonical form. Canonical form of the n by n system of equations can be obtained by performing n pivotal operations. Variable x I equal to 1 to n is eliminated from all equations except jth equation, for which a j I is non-zero. So, variable x I is eliminated from all equations except jth equation, and for jth equation the coefficient a j I is non-zero. So, general procedure for one pivotal operation consists of the following two steps. First, divide jth equation by a j I. Let us call it as E j prime. So, E j prime equal to E j by A j I. Now, subtract A k I times of E j prime equation from kth equation, that is E k minus A k I E j prime. So, by this you can convert the system of linear equations to its canonical form. That was about square system. What about non-square system, where you have m equations in n variables and n is greater than m? So, instead of square system, let us consider a system of m equations in n variables with let us say n greater than m. This system of equations is assumed to be consistent, so that it will have at least one solution. So, now I have this set of linear equations. Note that we have now m rows and we have now n variables. So, if you look at the coefficient matrix, it will have m rows, n columns. the solution vector x that satisfy the above equation cannot be readily obtained from the equations. However, it is possible to reduce this system to an equivalent canonical system from which at least one solution can readily be obtained. Now, we are talking about a situation where you have n variables and m equations, and let us consider n is greater than m. So, now let us see how we obtain the canonical form for such systems, so that one solution can be obtained. So, let us consider an example x 1 plus x 2 plus 3 x 3 plus x 4 equal to 7, x 1 minus 2 x 2 plus x 3 minus x 5 equal to 2. So, I have two equations and number of variables is 5, x 1, x 2, x 3, x 4 and x 5. So, 5 variables, 2 equations. So, let us convert this system of equation to its canonical form. First, we multiply row 1 by 2 and add to row 2. If we do that, you obtain this. Next, we divide row 2 by 3. You obtain this, and then multiply row 2 by minus 1 and add to row 1. Now, look at the system of equations that we obtained. If you look at this equation, you have x 1, then 0 into x 2, no x 2. So, x 1, 1 into x 1 plus 0 into x 2, and then you have x 3, x 4, x 5 and it has coefficients, then that is equal to 16 by 3. If you look at this equation, it is 0 into x 1 plus 1 into x 2, then plus x 3, x 4, x 5 you have along with its coefficients, and right side equal to 5 by 3. So, this equation, these two set of equations, if you look at only x 1 and x 2, they are in the canonical form. So, if I set x 3 equal to 4, x 4 equal, so if I set x 3 equal to 0, x 4 equal to 0 and x 5 equal to 0, I can obtain the solution as x 1 equal to 16 by 3, x 2 equal to 5 by 3. Note that you have two equations and 5 variables. So, setting arbitrarily any 3 variables to 0, I can solve for the remaining 2. So, by setting x 3 equal to 0, x 4 equal to 0 and x 5 equal to 0, I obtain x 1 equal to 16 by 3, x 2 equal to 5 by 3 readily. So, this is the equivalent canonical form that we discussed for square system n by n. We have a non-square systems, and for this x 1 and x 2 part here, I have that canonical form. So, the solution is x1 equal to 16 by 3, x2 equal to 5 by 3, x3 equal to 0, x4 equal to 0, x5 equal to 0. So, this is one solution. x1 and x2 are basic variables, x3, x4 and x5 are non-basic variables. So, the variables whose values we arbitrarily set to 0 are non-basic variables. Here x3, x4, x5 are non-basic variables and x1 and x2 are basic variables. The solution that we have obtained by setting non-basic variables to 0, that is x1 equal to 16 by 3, x2 equal to 5 by 3, x3 equal to 0, x4 equal to 0, x5 equal to 0 is referred to as basic solution, since all non-basic variables have been set to 0. This solution is also referred to as the basic feasible solution, since all basic variables are non-negative. If you look at the basic solution, the solution has all basic variables as non-negative. So, this solution is also referred to as basic feasible solution. Every corner point of the feasible region corresponds to a basic feasible solution. This is the fundamental building block for the simplex method. Every corner point for the feasible region corresponds to a basic feasible region, and this is the fundamental building block for the simplex method. Now, let us transform a set of equations to a canonical form in a more general case. So, we have the objective function z equal to c1 x1 plus c2 x2 up to cn xn, and we have m rows of constraints, that means m equality constraints in, and we have n variables and m is less than n. So, m is less than n, that means you have number of variables more than the number of constraints. So, this leads to infinite number of feasible solutions. So, you have a system where you have more variables, fewer equations. So, this leads to infinite number of feasible solutions, and therefore, the selection of best feasible solution that maximizes the objective function is not a trivial problem. It is not an easy problem. To generate the solutions, let us first use m variables to reduce the system to canonical or row echelon form by Gauss-Jordan elimination. So, you have m constants, n variables, and m is less than n. So, I can choose any m variables and then can reduce the system to a canonical form or row echelon form. So, the remaining variables I can set to 0 and can solve for m variables. Because you have n variables and m equations, in that case you can solve only for m variables. So, what we do is we take the first m variables x1, x2 up to xm and reduce the system to canonical or row echelon form by, say, Gauss-Jordan elimination method. So, by performing n pivotal operations for any m variables, say x1, x2, xm, called pivotal variables, the system of equations can be reduced to canonical form as shown. So, you have n variables and m equations. So, first focus your attention on first m variables. So, this part is similar to m by m square system. So, here I will have canonical form as discussed in m by m square system, and I can do this by doing the pivotal operations or doing these elementary row operations. The variables x m plus 1 to x n of the above set of equations is known as non-pivotal variables or independent variables. So, x 1 to x m are pivotal variables and x m plus 1 to x n are non-pivotal or independent variables. So, one solution that can be obtained from the above set of equation is x I equal to b I bar for I equal to 1 to m and x I equal to 0 for I equal to m plus 1 to n. So, how? All we are doing is we are setting x m plus 1 to x n as 0. Then the solution can easily be obtained as x 1 equal to b 1 bar, x 2 equal to b 2 bar, x m equal to b m bar and x m plus 1 equal to 0 up to x n equal to 0. So, one solution that can be obtained easily from the above set of equation is x I equal to b I bar for I equal to 1 to m and x I equal to 0 for I equal to m plus 1 to n. This solution is known as basic solution. The pivotal variables x 1, x 2 up to x m are also known as basic variables. Non-pivotal variables x m plus 1 to x m are known as non-basic variables. Basic solution is also known as basic feasible solution because it satisfies all the constraints as well as non-negativity criterion for all the variables. So, what we learned that we can convert a set of linear equations in n variables, m constants or m equations to an equivalent canonical form. And then if I take the first m variables as basic variables, the remaining m plus 1 to n variables as non-basic variables, I can set those non-basic variables to 0 and can solve for the basic variables. The basic solution is also known as basic feasible solution because it satisfies all the constants. With this, we stop our discussion on lecture 40 or week 8 here. In the next week, we will talk about simplex method and these concepts of basic solution, basic feasible solutions we will utilize for discussion on simplex methods.